Can you see the presentation?
Yes, we can.
Yes, we can.
We can
Yeah.
see that.
Thank you very much. Good morning to everybody. My name is Francesco Baldi. I am from University of Brescia, Italy, and together with Professoressa Alicia Salazar from Universidad Rey Juan Carlos in Madrid, Spain, we will give the lecture with title Fracturing Polymers, Basic Concepts and Testing Methods. The first part of the lecture will be given by me, whereas the second part will be given by Alicia. Concerning fracturing polymers, fracturing polymers has become a major concern when engineering plastics have begun to appear in critical structural applications. Now, in this lecture, in the first part of this lecture, I will review some basic principles of polymers in order to give an idea of the great variety of molecular structures and of microstructures and of course of their complexity. Very briefly, let's start from the definition of polymer. Polymer is a long molecule, a macromolecule, consisting of small units joined end to end. And polymers are divided into different families according to the type of the repeating unit. There is the family of polystyrene, the family of polycarbonate, glycerin, and so on. But focusing the attention on the type of chain of our polymers, in this part on the right of this slide, I have reported the three classifications of polymer chains: linear chain, branched chain, and cross-linked polymer. In a linear chain, the various repeating units are joined together in such a way to produce a continuous path from one end to the other end of the chain. Whereas, on the other side, in the cross-linked polymer, the network, this cross-linked structure, is at the basis of thermoset polymers, of thermosets. Think about epoxy resin, for example. Whereas thermoplastics consist in linear polymers and branched chains. I've put apart elastomers, which can be either thermoplastic or with lightly cross-linked structure, and of course they are capable of larger recoverable strain. I will focus the attention on thermoplastic polymers. The group of thermoplastics is larger than a group of thermosets, and also thermoplastics are more common than thermosets. Now, if I have a thermoplastic polymer, I can bring this process temperature, and this temperature, this thermoplastic is in liquid state.
Francesco, I think we're losing your audio a bit. Can you move closer to the microphone?
Yes, I will check it.
Thank you very much.
It seems my microphones seems okay. Can you hear me now?
Yes, we can. Yeah.
It's good now.
Okay.
Yes.
Thank you, Bamber. Now, thermoplastic polymer goes to the process temperature, passes in a liquid state, and in that liquid state it can be formed in order to obtain, after cooling, a part or a product. But if I consider the structure of that polymer when in the solid state, I can find either the semicrystalline structure or an amorphous structure. In a semicrystalline structure, macromolecules have the possibility to form regular patterns, regions with very high order. whereas in the amorphous structure, instead, macromolecules couldn't be able to weren't be able to form this regular pattern region. Now, if I consider polymer processing involves shaping, but shaping is intrinsically associated with material structuring at a macromolecular scale. And if we consider a part obtained, for example, in a semi-crystalline polymer, what we can obtain is that this part presents an homogeneous morphology, where regions characterized by a semi-crystalline structure are together with regions characterized by an amorphous structure, and this can have an effect on the performance of the product I'm considering. Nowadays, more and more often, thermoplastics are used as basis for compounds, and for structural application, practically the compounds consist in polymers filled with rigid particles or short fibers. Now, if I consider processing of compounds, shaping is associated to material structuring, but material structuring does not occur only at a macromolecular level, but also at a larger scale, resulting in specific distribution and orientation of particles, which add another degree of complexity to our structure. Now, if I look at this image on the left, where we can observe some glass fibers embedded into a polymer matrix, I may wonder, what about the continuum assumption that is at the basis of continuum mechanics? Nowadays, thermoplastic polymers are used practically in all the industrial sectors, from automotive to construction and building, from biomedical to electronics, from industrial design, from design to packaging. And we can find thermoplastic polymers in products with thick parts, as well as in products very thin films, which have a thickness that is down to 5-10 microns, for example. If I switch to the mechanical behavior of polymeric materials, the first thing that we have to say is that the mechanical response of a polymeric material can change remarkably by relying from polymer to polymer. And just to give an idea, I have reported this graph in which there are two stress strain curves obtained from tensile test on a polymer 6, the green curve, and on a compound that is based on that polymer 6, and this is its stress strain curve represented here as a brown curve. Now, the difference between is clear. On one side, we have the compound that exhibits a brittle behavior characterized by a strain at break that is around 4%. Whereas if I consider the polymer 6, I can observe an elongation at break that is around 60%, that is reached after an extended reformation region that is governed by specific mechanisms, specific deformation mechanisms, which activated at yielding here in the area highlighted in yellow. Now, it is important to underline that in plastics, plasticity is not directly related to irreversible deformation, but rather it is related to the occurrence of specific deformation mechanisms, which are shear yielding and crazing. Therefore, when we deal with polymers, exhibit in tension either a very brittle behavior, degrees of ductility. When we talk about polymers, we talk about viscoelasticity. Due to their macromolecular nature, polymers are viscoelastic at all temperatures. They never behave as simple elastic solids, nor as simple viscous fluids. When we say that they are viscoelastic, to a polymer in service, we have to consider not only the level of stress and strain, but we have to consider also the time for which that stress and strain will be applied to the material when it is in service, and also the temperature. In other words, we have to consider the history experienced by the polymeric material when in service. In this slide, I have referred to a thermoplastic amorphous material and to its relaxation modulus. And in this graph here, I plot the variation of the modulus, that is an index of material stiffness, with the temperature. We can easily observe that from a modulus of plus or minus 1 gigapascal, the material goes to a modulus that is around 1 megapascal, that is typical of rubber at room temperature. This transition, where we observe this clear decrease in modulus, is the glass transition temperature. But it is interesting to observe that if I plot the modulus, the relaxation modulus, as a function of the time for which I am observing the mechanical response of the material, that is practically a time of experiment, and I keep the temperature fixed, for example, to 0, I can observe a similar transition. Now, at mid-60s, the combined action of temperature and time of experiment, the viscoelastic response, of a viscoelastic material, of course, was described by referring to a dimensionless number, that is the Deborah number. Now, if I plot the relaxation modulus as a function of the Deborah number, I can observe that there is a region that is highlighted, that is indicated here as a green area, that is the region corresponding to short experiment time and low temperature, in which region, if I'm able to keep the material in that region, I'm quite far from this transition. Now, this region corresponds to the high values of Deborah number, and this region is the region where the material exhibits a prevalently elastic material. Now, if I can stay in this region, in the green region, I can apply the testing approaches for time-independent materials also to our polymeric materials. Therefore, I get that the material is viscoelastic, of course, but at least I can try to apply the testing approaches specifically developed for time-independent materials. Let's arrive to fracture mechanics. Now, concerning fracture mechanics, we know that we can count on several fracture mechanics schemes. Time-independent materials in quasi-static conditions, and that is valid if the non-linear deformation region is confined at the crack tip. Within the linear elastic fracture mechanics, we have the toughness parameter, the fracture parameter, which are the K, the stress intensity factor, and the energy release rate. Then we have elastic plastic fracture mechanics that was developed for nonlinear time-independent materials, and the fracture parameters are the crack tip opening displacement and Reynolds J integral. More recently, it was fracture mechanics extended also to viscoelastic and viscoplastic materials, and therefore to time-dependent materials. And in this case, we can count on C-star integral parameter and viscoelastic J, and also it was possible also to consider dynamic effects in this test. Now, this is, let's say, the tree of fracture mechanics. But which scheme of fracture mechanics can I apply to polymers? Now, the choice of the fracture mechanics scheme polymers is based on the specific polymeric material examined, and in particular its mechanical behavior. And we have to forget also that we have not to forget that also the thickness plays an important role. And then I have to take into account the in-service conditions, as I told before. I have to consider the temperature.
Francesco, you need to be at the microphone more.
Okay, thank you.
Good.
The in-service condition, therefore the temperature, the loading history, and also the environment where the material will work when in service. Now, if I consider the amorphous materials considered, examined in two previous slides, and I consider the green region here at high levels of Deborah number, okay, in this region I might try to apply the linear elastic fracture mechanics and the elastic plastic fracture mechanics approaches developed for time-independent materials. Therefore, the fracture parameters developed within linear elastic fracture mechanics and elastic plastic fracture mechanics might be suitable. In this graph here on the left, I refer to an amorphous polymer simply because it is simpler to describe, but similar consideration may apply also to a semicrystalline polymer. Now, just to give you an example, in this slide, I have reported some data, some fracture toughness data obtained in mode 1 of fracture opening mode to polymers according to the linear elastic fracture mechanics and to the elastic plastic fracture mechanics scheme. In this box on the left, we can read data of T1C and G1C. C means that it's at fracture initiation, for a polymer 6,6 and for a compound polymer 6,6 with 50% of glass fibers. Okay, we can read that for the polymer 6,6 I have a value of T1C that is around 3 megapascal per square root of meter, whereas for the compound 8.6. But the number is not important in this context. What is important is that I succeeded in the application of a linear elastic fracture mechanics developed for time-independent materials to polymers. Instead, here in the box on the right, I have reported a JR curve that is a curve, resistance curve, in which the values of J are plotted as a function of the crack advancement delta A value of J at fracture initiation of 4.3 was determined, and this curve refers to a rubber toughened polybutylene terephthalate. Both this rubber toughened PBT and this compound were developed for automotive applications. Of course, also in this case, let me underline that we could successfully apply a protocol, a method developed within the elastic plastic fracture mechanics. Of course, on this PBT, I couldn't apply the linear elastic fracture mechanics, not because of the fact that it is viscoelastic, but simply because of the fact that the degree of ductility exhibited by this material was too high for the application of the linear elastic fracture mechanics. I mean that the linear elastic fracture mechanics approach could not be considered valid. Now I would like to focus the attention on some peculiarities related to fracture testing of polymeric materials. Okay, if I consider mode 1 opening mode, test on notched specimens, I consider, of course, specimens with notch inside. This image shows a single-edge notched in bending specimen. Therefore, I prepare the specimen, I notch the specimen, I execute the test in quasi-static conditions. Of course, I have to take into account always the time. They are viscoelastic, and I cannot forget this fact. From this test, I obtain the loading curves, and by using specific dimensions of the specimens and additional data determined from analysis on the broken specimen, I can determine the values of the fracture toughness parameters, T1, J1, J1, depending on the method I'm using at fracture initiation. So, concerning notching, In a polymer, the notch can be introduced either via contact technique or a contactless technique. The important thing is that the notch has a very sharp tip, and of course the region in front of the tip is defect-free, in the sense that no mechanical or thermal damage has occurred. Now, if you look at these photos of notches taken on non-tested specimens, we can observe that this picture on the left refers to an high-density polyethylene. In this picture, I have no damage. I cannot see any damage in front of the tip of the crack, in front of the tip of the notch. Whereas in the other two photos that refer to an epoxy resin and to a styrene acrylonitrile polymer, I can observe some damage of the crack tip. Here on the right, for example, there is evident plastic deformation that was introduced during notching. We have to avoid this situation. Sharp notch, yes, but with the material in front of the notch without any sign of damage. Of course, I have to consider time matters. And in particular, when we apply, as it will be described by Alicia in the second part of this lecture, when we apply the linear plastic fracture mechanics and the elastic plastic fracture mechanics, I need to refer to yield stress data. Now, in the choice of the yield stress data, I have to consider that the stress is the experienced during the test. Therefore, I have to refer to the time to fracture in order to choose a value of yield stress determined with a time to yielding which is quite similar to the time to fracture. Similar consideration applies also when I have to perform energy correction test, for example, for the specimen indentation, that is quite important when we deal with plastic polymers. I have to refer to the time to fracture in order to obtain data, energy data, which might be used data obtained in fracture test. Another thing that I would like to point out is that in a stable crack propagation process that is typical of polymers, the crack advancement different from what is on metals, in the sense that on metals I can determine during fracture in a stable crack propagation process, I can determine indirectly the crack length by measuring the unloading compliance. With polymers, it is not possible, since due to the fact that the polymeric response depend on the time, on the history, the unloading curve and the reloading curve are not superimposed. Another problem we have to face when we deal with polymer is that the measurement of the crack advancement that is in stable crack propagation test, that is optical and that is made on specimen properly brought to complete fracture is not easy, in the sense that the crack front, which divides the region, the fracture, the fracture area produced during the fracture test, remaining area obtained during the complete breakage of the specimen, cannot be easily identified. In fact, some techniques which are not based on the crack advancement measurement are being under consideration in our EasyTC4 table. Another aspect that I would like to remark concerns specimen thickness. Of course, also with polymers, we have the transition from plane stress to plane strain at crack tip, with plane strain fracture toughness that is the size-independent material property. Just to underline the fact that in polymers, if we compare the behavior of given material characterized by a very low thickness, the behavior of the same material, but a part characterized by very high thickness. Just remember properly the structure of the materials in the two different products. On one hand, a product characterized by very low thickness, and on the other, very thick specimen, different. and gives and this adds another degree of complexity to the analysis of the specimen thickness effects on the fracture response of polymeric material. Now I have finished my first part, and I invite Alicia to continue. Thank you for your attention.
Okay, thank you very much, Francesco, and good morning to everybody. Francesco, if you don't care, I'm going to share the presentation from my computer. So I'm going to...
If you want, I can...
Okay, I'm going to see.
Okay.
Okay, can you see my presentation?
Yes, Alicia, that's very clear.
Okay, thank you. Well, in this part of the presentation, I'm going to focus on the explanation of the test methods for the fracture characterization of polymers. And I'm going to start with the procedure for the characterization according to the linear elastic fracture mechanics approach. The phenomenological aspects of this type of fracture are linear and elastic mechanical response as observed in this low displacement record of a cracked specimen. I'm sorry, I'm going to use the laser. Okay, sorry, that's it. And the second aspect is that the local deformation at the crack tip is very small. In most cases, there is unstable crack growth propagation as shown in this plot. But in some cases, there can be a stable crack growth, but several restrictions on linearity must be imposed for characterization according to this approach. Fracture is defined by the crack growth initiation, and in polymers, this behavior can occur at temperatures lower than the glass transition temperature and or high strain rates. The fracture parameters, as already told by Francesco, are the critical stress intensity factor, K1C, and the critical energy release rate, G1C. The subscript 1 corresponds to the opening crack opening mode. And the standards for the determination of these two parameters are the ISO 13586 and ASTM T5045. The aim of this test is to characterize the fracture toughness of plastics in terms of the critical stress intensity factor, Q1C, and the critical energy release rate, G1C, at fracture initiation and at low speed. The scheme assumes linear elastic behavior of the crack sample fulfilled in the low displacement record. The crack of the specimen must be sharp to ensure a minimum value of the fracture toughness. A state of plane strain at the crack tip is required, so the thickness must be large enough to guarantee this state. And the plastic deformation at the crack tip, shown in dark blue in this plot, must be very small in comparison with the stress intensity factor dominated zone, that is the area ahead of the crack tip and shown in light blue in this plot, and specimen's dimensions such as the thickness B, the ligament defined as the width minus the crack length, and the crack length A. The recommended specimen configurations are compensation and 3-point pen geometries. The reason is that they require smaller sizes to achieve plane strain conditions, very important, than other configuration. Normally, the material is supplied in form of sheet, and the specimen thickness should be identical with the sheet thickness. The width, W, is twice the thickness, B, normally, but in some cases, the width can range between 2 and 4 times the thickness in the 3-point band specimens. The two right photos show the experimental setup for the 3-point band and the compact tension configuration. The machine notch must be sharpened, and the total final crack length after sharpening must be between 0.45 and 0.55 times the width. Notch sharpening is a very difficult task, and more details will be given this afternoon in the talk Notching for Fracture Testing of Polymers. The test is performed at room temperature and normally at a cross-head speed of 10 millimeters per minute, and the loading time and the loading rate must be noted. The load line displacement record is obtained, as is shown in this graph, and in the ideal case, I want to show, the load displacement record is linear with a sudden drop of the load at the very instant of crack growth initiation. In this case, the maximum load is used for the determination of the fracture parameters. But in most cases, there is no linearity in the curve, and some restriction must be imposed for the application of this approach. Firstly, I'm going to describe how to determine the critical stress intensity factor Q1C. And for this, it is first necessary to calculate a conditional result, KQ, which is obtained from a load named PQ. And to attain this load, the following construction on this test record is needed. First, draw a best line to determine the initial compliance, C0, dotted line in black. Secondly, draw a second line with a compliance 5% greater, dotted line in blue. And the intersection of this straight line with the load curve is defined as P5%. If the maximum load over P5% is smaller than 1.1, the linearity criterion is fulfilled. Otherwise, the test is not valid. Once the linearity criterion is satisfied, we have to define PQ. And we have two options. The first one, if the maximum load, Pmax, is higher than P5%, then P5% is equal to PQ. On the other hand, if the maximum load is lower than P5%, then PQ is equal to the maximum load. For the determination of the fracture parameters, we also need the value of the initial crack length, and this is obtained from the fracture surface. This photo shows the fracture surface of an epoxy resin where the machine notch, the sharp notch, and the stable crack growth are visible. The total crack length after notching and no sharpening is obtained as the average of 5 values, 2 measured on the surface, 1 at the center of the specimen, and 2 values measured midway between the surface and the center of the specimen. KQ is calculated using this expression. Apart from PQ, B is the thickness, W is the width, and F is a calibration factor dependent on the crack length to width ratio, alpha. This slide shows the calibration factors for the 3-point bending specimen with a span to width ratio of 4 and for the compact tension specimen. Finally, for the validity of KQ must be checked by the size criterion. The thickness, the crack length, and the ligament length must be higher than this value, where the square of KQ over the yield strength is proportional to the plastic zone size. If this criterion is fulfilled, then KQ is equal to Q1C. Otherwise, the test is not valid. Typical values for brittle solids such as epoxy resins are in the range between 0.5 and 3 megapascals square root meter. For determination of G1C, we determine a conditional value, GQ, with this expression, where UQ is the energy computed as the area under the load displacement curve up to the very same load point used for Q1C determination. Phi is a calibration factor shown in this table for the 3-point bend and the compact tension specimens. The following cross check must be performed. The value of the Young's modulus E over 1 minus a square Poisson's ratio should be larger than the square Q1C over GQ. The maximum difference should be of 15%. If this is fulfilled, then GQ is equal to the critical energy release rate. Otherwise, the results should be inspected for possible errors. The Young's modulus and the Poisson's ratio are obtained from mechanical tests such as tensile tests carried out at the very same experimental condition than those used for the fracture characterization. Typical values of G1C for brittle polymers are in the range between 17 and 200 joules per square meter. Next, I'm going to describe the fracture characterization according to the elastic plastic fracture mechanics approach. The phenomenological aspects are non-linear mechanical response as observed in this low displacement record of a typical ductile fracture on polymers. Large amount of crack tip plasticity. This can be observed in these photos as a whiting region ahead of the crack tip, as well as crack tip blunting, a stable crack growth, and the fracture property in this case is not a single value. It's a fracture resistant curve in which the fracture parameter is a function of the crack growth extension. Finally, this type of fracture occurs in tough polymers or in general at temperatures higher than the glass transition temperature and a low strain rate. The fracture parameters are the J integral and the crack tip opening displacement, or CTOD. And taking into account the stable crack growth, the fracture parameters are the JR curve or the CTODR curve. In this course, only the determination of the JR curves of polymers is described, and the standards are the ASTM D6068 and the ASTM, E1820. In this slide, I want to describe briefly the JR curve. This curve displays the J integral values that we'll see later how to calculate them versus the crack growth station, delta A. Two regions are distinguished. Region 1 in green, the crack remains stationary, but crack tip blunting occurs. The crack growth due to blunting is described by a strike line given by this expression, where M is a constraint factor which can have values between 1 and 3, and sigma 1 is the yield strength. In region 2, in blue, real crack growth occurs, and the crack growth is described by a power law with an exponent n less than or equal to 1. The initiation value of the J integral of fracture toughness is obtained as the minimum of the following values. J blunting, JBL, is obtained as the intersection of the blunting line with the GR curve, and J 0.2 is the J value of the crack growth station of 0.2 millimeters. This value is completely arbitrary, but it combines two facts. One, is small enough to be close to the crack growth initiation, and secondly, it is large enough to be measured by optical means. The aim of this test method is to determine the mode 1 J integral versus crack growth resistant curve for polymeric materials at a low speed. The conditions are: the applied load must increase steadily. The material should be and should not be unloaded during the test. The crack must be sharpened to ensure minimum values of fracture parameters. A state of plane strain at the crack tip is required. So the specimen thickness must be large in comparison with the chill zone. The material temperature must remain constant during testing, and the crack station must be measured via optical means from the fracture surface. The most common approach for determining the JR curve of a polymer is the multiple specimen method. In this method, a set of identical specimens are loaded to different displacement and then unloaded to attain different crack stations. Each test is to develop a single point on the JR curve, and a minimum of 7 valid tests are needed. The specimen configurations are the very same as those described in the linear elastic fracture mechanics approach. The machine notch must be sharpened, very important, and the length of the pre-cracked specimen should satisfy the following requirement. The initial crack length A0 to the width ratio must be in the range between 0.55 and 0.65. The tests are normally performed at room temperature and at gross head speed of 1 millimeter per minute, and the procedure consists on, first, loading the specimen to a selected displacement to attain a certain crack station, and secondly, unloading the specimen, mark the crack front, and break the specimen to exposure the fracture surface. This is a very important part indeed. The result is a low displacement record where U is the energy obtained from the area under the low displacement record up to the displacement corresponding to the test termination. For the termination of the JR caps, we also need the measurement of 2 crack lengths. The initial crack length, A0, includes the machine notch and the sharp notch and the sharp crack, and the stable crack length station, delta A. This micrograph shows the fracture surface of a ductile polymer as an ethylene propylene block polymer, where it is observed the sharp crack, the stable crack station, here it is, the ductile fracture or the plastic deformation, and then a stable failure. For each specimen, the J integral is calculated using this relationship, where U is the energy already described, B is the thickness, W is the width, A0 is the initial crack length, and eta is a calibration factor which has a value of 2 for the 3-point band specimen, and for the compact tension is calculated through this expression. For the construction of the JR curve, we use the J integral values and the crack extension delta A values to obtain a plot of the fracture resistance against the crack growth. There are 2 exclusions lines in red, one at 0.05 millimeters. Only the data beyond this line are considered valid, and the other one is at 0.1 times the initial and crack ligament. Beyond this limit, the J values may not be valid. To ensure that the data points are evenly spaced, the interval is between the 2 exclusions line is divided into 4 equal sections. Since there is an interest in determining the fracture toughness or the fracture initiation parameter, 3 points are recommended in the first section, 2 in the second, and 1 in the third and fourth section. The resistance curve is fit to a power law, shown in blue. Finally, for the determination of the J1C, the energy at crack growth initiation, we compute the minimum value of J blunting in green, obtained as the intersection of the blunting line with the JR curve, this point, and J 0.2, that is the J integral at a stable crack growth of 0.2 millimeters. In this case, J1C is equal to J blunting. To guarantee plane strain values, the following size criteria must be fulfilled. And finally, values of the energy at crack growth initiation of a ductile polymer as an ethylene propylene block polymer can range between 10 and 20 kilojoules per square meter. I would like to finish describing briefly the test method for determining the toughness of thin plastic films, very much used in quite a big number of applications. The graph shows the ductile behavior of a crack film with plots, with photos, showing different instances of the fracture process. The phenomenological aspects of this type of fracture are gross ductility in plane stress state, change, it's a film, full yielding of the ligament before crack growth, and the approach applied for the fracture determination is the post-yielding fracture mechanics, and the fracture parameter is the essential worker fracture WE. The details of this test method can be found in this reference. The essential worker fracture approach is based on the hypothesis that total energy involved during the ductile fracture of a cracked film is divided into two terms. The essential worker fracture, WE, that is specific to the fracture of the material in the fracture process zone, shown in dark blue in this plot, and a non-essential worker fracture, WP, which is related to gross plastic deformation occurring outside the fracture process zone and shown in light blue in this plot. This plot shows evidently a cracked film. So the total energy absorbed can be written as follows, where L is the ligament length, T is the sheet thickness, and beta is a shape factor associated with the dimension of the plastic zone in the outer process zone. Normalizing by the ligament cross section, we obtained the following expression, where the parameters, the fracture parameters, the essential worker fracture and the non-essential worker fracture can be obtained from the best fit linear regression of data of a series of broken specimens plotted in a diagram of a specific total fracture energy versus the ligament length, as shown in the next slide. I don't want to skip this, is that for films characterization, normally double-edge notch tension configuration is employed, as shown in this plot. At least 20 specimens are tested with different lengths. This graph shows the low displacement records of specimens with different ligament lengths of ethylene propylene blocker polymer films with 0.5 millimeters in thickness. One important feature is the self-similarity of the low displacement records of the films with different lengths. And for each curve, the total energy is calculated as the area under the low displacement record, and the specific energy is obtained dividing by the ligament cross section. This graph shows the specific worker fracture energy versus the ligament length. The fracture parameter is obtained from linear regression, and in case of ethylene propylene blocker polymers, the essential worker fracture can range between 30 and 40 kilojoules per square meter. And in this slide, it's collected some literature regarding this presentation. Thank you very much.